Hey everybody, welcome to this tutorial slash review on NMR. I wanted to go over some of the concepts behind NMR just to review because oftentimes it's been a while since students have done any NMR practice. So I'll be going over some of those. Not everything I discuss will necessarily be something you need to know for a test, but I think it will be helpful in understanding these better and helping you fill them out. And then I'll go over what we expect on these, what a finished product ready to be turned in should look like. With this class, we actually don't run our own NMRs. You're just given the sheets for them. They've already been done for you. Your job is to figure out which molecules go to each NMR and then be able to identify and label the peaks correctly on both the H NMR and the carbon NMR. These you can find online on Learning Suite. So if you go to the Content tab here on Learning Suite, down to Course Documents, there's a little miscellaneous tab underneath that. In here you'll find different helpful documents or PDFs for things throughout the semester to help you fill out your lab write-ups. What we'll be looking at is the spectroscopy packet. If you open that up, it'll give you all of the NMRs for the organic reagents and products that are used throughout this lab. And that's what we'll be focusing on. So if you go there and open it up, you'll see the sheets, and at the top right hand corner you'll see the name of the lab that we're doing. So in this case, we're doing the Fischer esterification lab. And you'll see 3 sheets that have that name on them because in the experiment there are 2 organic reagents and 1 organic product produced. Water is an inorganic byproduct of the reaction, so there's not an NMR for that, but there'll be an NMR for the acetic acid, isopentyl alcohol, and the isopentyl acetate. Now, each page on this PDF is the NMR for some specific compound from an experiment. And each page is split into 2 halves. The top half is for the H NMR of that compound, and the bottom half is the carbon NMR for that same compound. You'll also be given some additional things every once in a while. So on the top half, if you look there, you'll see an additional box. And that is just a zoom in of the H NMR peaks, just so you can see the splitting a little bit better and see those peaks slightly better than on the zoomed out version. And then on the bottom half, there's another graph or box there. That's called a 2D NMR. We'll get back to that. We'll discuss that a little bit later in this video. Now for this NMR, we are actually looking at the product of Fischer esterification, the isopentyl acetate. Now I'm just straight up telling you which compound it is. That's going to be part of your job on these, is figuring out which compound goes to which NMR and then labeling the peaks. But for the purposes of this video, we haven't talked about the strategies yet, so I'm just going to kind of show you. But that's what you should start out, is figure out which structure goes to which NMR, draw in the structure so that we can start labeling our unique hydrogens on that structure, and then figuring out which peaks go to which hydrogens. For consistency purposes, let's just have everyone label their hydrogens the same way. We're going to label them as letters, and then we'll label our carbons as numbers just to distinguish them well enough. So we'll go ahead and start labeling our hydrogens on this molecule, starting left to right. So if we look at the hydrogens all the way to the left there, we'll label those as A. All 3 of those are equivalent. They're not in any different kind of chemical environment, and so we can label them all as the same letter. And you don't have to draw in the hydrogens and label them each as hydrogen A. If you do it like I've shown here, we understand exactly what you're saying. You're just saying that all of them are A. And now we can label the rest of our hydrogens just moving down the molecule to the right. We have 2 equivalent hydrogens next to the oxygen that we'll label as B, and then 2 equivalent ones that we'll label as C. And then there's a hydrogen in between those 2 methyl groups that we can label as D. And then the iso group there, all the hydrogens coming off are equivalent, so we'll label them as E. And you don't have to label both of the methyl groups that way. You can just label one of them as E, and that shows that you understand that the other hydrogens coming off of that other methyl group are equivalent. And as you can see now, there are 5 unique hydrogens on this molecule and 5 H NMR signals. So that's a good sign that we picked the right structure for this NMR, especially since I told you it was the right structure. Now, you may be wondering what these other two small peaks or signals may be. They're not actual protons from our molecule, but they are produced by compounds that are used to run these NMRs. So the first one is TMS, which stands for tetramethylsilane, which is used as a standard to compare the rest of the peaks to. The protons on that molecule are extremely shielded, and so the signal that they give off is set at 0, and all of the other chemical shift values that we see for the rest of the peaks are in relation to the signal that that one gives off. And the other peak that we see there at around 7.3 is from a solvent that is commonly used on NMRs, which is CHCl3 or chloroform. Now, the actual solvent that's used is deuterated chloroform, which would be CdCl3, and that wouldn't show up on a proton NMR because deuterium isn't a proton, but deuterated solvents aren't 100% deuterated, so some of the CHCl3 is still there, and that's what's getting picked up on this proton NMR. You will see these basically on every NMR that we do, and you need to have them labeled. Plus, they'll show up on your test, so I would recommend starting to memorize where they'll show up, the values that you see them at, and just labeling those solvents every single time. Okay, so now we'll look at the bottom half of the page and do the same thing for the carbon NMR. We'll draw the structure of our molecule again, and we'll go ahead and label all of the unique carbons as numbers starting left to right, so it'll look like this. There are 6 unique carbons on this molecule. And if you look at the peaks, you actually count 7, but this little grouping of peaks around 77, again, isn't an actual carbon from this molecule. It's from the solvent used. This time, this would be the deuterated chloroform or CdCl3. So there are actually 6 unique carbons and 6 unique peaks. That works out great for this molecule. And now that we have our molecules labeled, we can start analyzing the peaks and labeling them accordingly. To do that, I'm going to talk about some of the concepts behind NMR and some of the strategies to labeling these. I'm going to be focusing on HNMR because it's slightly more important for this course, but some of the same concepts will still apply to carbon NMR when we talk about that. The first, and I'd say the most important thing to look at is chemical shift. Where on the x-axis on these spectra are the peaks going to show up? Are protons going to be more shielded or de-shielded? And you can start learning ranges for where protons on specific functional groups usually show up on the NMR. Generally, electron density is what affects where those protons end up. The more electron density they have around them, the more they can shield themselves from the applied magnetic field from the machine. Basically, what's happening is that each proton on these molecules has its own magnetic spin. And when we put the molecules in the NMR machine, it applies a magnetic field onto the molecules, and the protons can either align with the magnetic field, like we see in A, or against the magnetic field, as shown in B. There's a specific energy attributed to each of these spin states. When it aligns with the magnetic field, it decreases in energy, and when it aligns against the magnetic field, it increases in energy. So these protons resonate in between these two energy states as they alternate aligning with or against the magnetic field, but as they drop down in energy, there's a quantized amount of energy that is released, and that energy in the radio frequency of the electromagnetic spectrum is what produces the signals or the peaks that we see on our NMRs. Those signals that are produced are then compared to the signal produced by TMS, and the difference between them is what we call the chemical shift. So in this case, looking at the 9 hydrogens that produce that peak, we would say the chemical shift would be 290 hertz. Now, for conventional purposes, the chemical shift is converted into parts per million rather than keeping it in hertz. And the way that we do that is by dividing the frequency of this signal in hertz from TMS, so in this case 290 hertz, by the applied spectrometer frequency in megahertz. So this machine was applying 200 megahertz, so if we put that into the equation, we get out 1.45 parts per million. And these are the values that we see on the x-axis of our NMRs. They're always going to be in ppms. And this is where electron density comes into play, because under an applied magnetic field, the circulating electrons actually induce their own magnetic field in opposition to the applied field. And so the effective magnetic field that the proton feels is actually slightly less. The more electron density it has around it, the stronger the induced field, and so it's more shielded from the applied field. So when we talk about shielding means more electron density. It's going to be further to the right, so a lower ppm value or up field. And when something has less electron density, it's going to be deshielded. It's going to have a higher ppm value, and it's going to be more to the left or down field. This language will be helpful because as we analyze peaks, we'll say things like more deshielded or more shielded. So when looking at our own NMR here, the peak furthest to the left, we'd say that's the most deshielded proton, and then the peak to the furthest to the right would be the most shielded. So there are actually fairly specific ranges for the values of chemical shifts for protons depending on what functional group they are attached to. And on Learning Suite, there's a document that kind of gives you those ranges that I think is super helpful. So if you go to the Content tab again, looking under the miscellaneous part of that tab, you'll see a document there that says Spectroscopy Help Sheet. I think this is super helpful. It gives you the ranges for a lot of the common groups that we'll see in our molecules that we use in the lab. So you'll see things like carboxylic acids, aromatic rings, alkenes, stuff like that. And they'll have the ranges for where we expect to see those protons show up. On this sheet, you'll also see ranges for carbon NMR peaks. You'll see some of the key solvents, a few of which we've already talked about. And then you'll also see peaks for infrared spectroscopy, which won't be discussed in this video, but is also an important part of the lab. Another tool you can use when analyzing peaks is called splitting. This occurs when two neighboring protons are coupled to each other, meaning that the spin state of one proton actually affects the NMR signal produced by the other. The range for coupling is limited. We only really see a significant effect when the protons coupled to each other are one carbon away from each other, like we see here with HA and HB. So we'll use this molecule as an example, since HA and HB only see each other as neighbors and no other protons. So let's analyze A, and we'll look at its neighbor, hydrogen B. Hydrogen B has its own spin state. It can be either aligned with the applied magnetic field or against it. And depending whether it is aligned with or against, that will actually change the effective field that hydrogen A experiences. Here's the NMR for this molecule. We'll still be analyzing hydrogen A, but we'll be looking at the spin state of hydrogen B and how that affects the signal for hydrogen A. So if the spin state for hydrogen B is aligned with the magnetic field, that actually slightly increases the effective field that hydrogen A feels, and so it pushes it slightly more downfield. If the spin state of hydrogen B is against the magnetic field, it slightly decreases the effective field that hydrogen A feels, and so it pushes its signal slightly upfield. Now, since all of the molecules in the NMR machine have a 50-50 chance of having their spin states for hydrogen B be either aligned with or against the magnetic field, that means hydrogen A gets split pretty evenly into two peaks, and we call that a doublet. We can analyze our molecule in the same way. So let's look at B, hydrogen B, for example. It has two neighboring protons, each with their own spin state. They could be aligned with or against the magnetic field. And hydrogen B will be split into a triplet depending on how those neighboring hydrogens are aligned. If the spin states for the neighboring protons are both aligned with the magnetic field, then the signal for hydrogen B is slightly to the left. If the spin states for the neighboring protons are different from each other, then we get a peak right in the middle. Notice that there are two ways that we can show those spin states being different. So there's twice as much probability that that will occur, and that's why the signal in the middle is about twice as high as the other two signals. And then if both the spin states are aligned against the magnetic field, then the signal for hydrogen B is going to be slightly to the right. Obviously, this can get a lot more complex as you increase the number of neighboring hydrogens, but a good rule of thumb is the n+1 rule, where n is equal to the number of neighboring hydrogens. So for example, if some proton had 4 neighbors, you would do 4 plus 1 and expect that signal to show up as a quintuplet, or however you would call it. It would show up as 5 peaks. Now, please be aware that this rule doesn't always work. There are going to be cases where, neighboring hydrogens might have different coupling constants, or there aren't optimal bond angles or whatever. Basically, you're going to see some crappy splitting where using this rule isn't going to help you at all. But it's good to start off, and at least on our NMR that we're going to be analyzing, the splitting is really clear, and you could probably figure it out just by using splitting. The next tool I'm going to talk about is called integration, which basically just tells you the number of hydrogens that are attributed to each peak that we're analyzing. So if you've taken calculus before, you know that integration is used to find the area under some curve. And that's all we're doing here. We're looking at the line above each peak and measuring the area underneath it, or basically the distance from the bottom as it jumped up to the top. That distance there tells you how many hydrogens are attributed to the peak below. In this example, the peak that we are analyzing is attributed to these hydrogens here, which makes sense why they have an integration of 2, because there are 2 hydrogens attributed to that peak. To show this on our molecule, I'm actually going to go ahead and start labeling the peaks, just because the line of integration on this NMR doesn't give you a numerical value, and so the only real way that we can analyze it is relative to each other. Let's start by looking at the furthest left peak around 4. It's a triplet, so out of the hydrogens on our molecule, B is the only one that would be able to produce a triplet because it has 2 neighbors. And if we look at the ranges for where that would show up, it's right within the 3 to 5 range because hydrogen B is bonded to a carbon that's directly bonded to an oxygen, and that's why it shows up around 4. So let's go ahead and label that peak as B. And you can label it just like this. You don't have to draw any arrows or anything messy. Just write the letter next to the peak, and that way it'll keep it nice and clean. If we look at the integration for that peak, we have 2 hydrogens that we've labeled as B. So the line of integration there should be representing an integration of 2. Now that we know that, we can analyze the integration of a different peak like this one. If we look at its integration, it seems to be about half the size of the integration that we analyzed for B. So that would mean it would have an integration of 1. Now if we look at our molecule, there's only one kind of hydrogen that would have an integration of 1, and that's hydrogen D. We could also look at the splitting for hydrogen D, which would also give us a clue to which hydrogen that is. It's hard to tell because some of the peaks on the far end start getting really, really small, but it's got lots of splitting. It's a multiplet, and there's only one hydrogen that could give us that many peaks that has that many neighbors, and that has to be hydrogen D. So we can go ahead and label that now as well. The last tool that you can use is just counting the number of unique hydrogens, which I've kind of shown already. This helps you identify which molecules go to which NMR. Sometimes it doesn't always work out so well because there can be overlapping peaks. But if there are overlapping peaks, the number of unique hydrogens can help. For example, if you have a molecule that has 8 unique hydrogens on it, but you only see 5 peaks, odds are some of the hydrogens on that molecule have similar chemical shifts where their signals would actually overlap with others. And you would expect to see some of those peaks have a really big integration because there are multiple hydrogens attributed to those peaks. Okay, let's go ahead and wrap up the HNMR here. Let's look at this next peak around 2 ppms. It's a singlet, and the only hydrogen on this molecule that doesn't have any neighbors is hydrogen A. Plus, if we look at the chemical shift from 2 to 3, that is for any protons that are alpha to a pi system. So they are 1 carbon away from some kind of pi system, like an aromatic ring, an alkene, or in this case, a carbon that's double bonded to an oxygen. Plus, its integration is slightly bigger than the integration of hydrogen B, but not quite twice as big as it. So that looks like it's going to be an integration of 3, which all just confirms that that is hydrogen A. Now let's look at the farthest right peak. It's a doublet, meaning that this hydrogen only sees one neighboring hydrogen, and it has a very large integration, looking to be around 6, so that has to be hydrogen E. And this leaves our final peak to be hydrogen C, which makes sense because it's a quadruplet and has an integration of 2. You do not have to label both the zoomed in and the zoomed out version of the peaks like I've done here. I was just being consistent through the video, but as long as you have all of the peaks labeled in the end, that's all that matters. Okay, let's wrap up the carbon NMR now. The carbon NMR is a little bit different than the HNMR because there's no splitting and there's no line of integration, but we can use similar concepts in chemical shift. It's not as specific and helpful as HNMR, but if we have some more outlying peaks like the carbonyl carbon here, that can be useful. The carbon double bond to an oxygen is the most deshielded carbon that we see, and it's always above 160 ppm. So we can go ahead and label that peak there as carbon 2. And for the rest of the peaks, we actually have this really cool 2D NMR up here. That's going to be very, very useful. It shows coupling between hydrogens and the carbons they are directly bonded to. So on the y-axis, we have the HNMR, which we've already labeled, so we can put in the letters there. And on the x-axis, we have the remaining peaks from the carbon NMR. So how this works is that each hydrogen is connected to the carbon that it's directly bonded to through a spot on this 2D NMR. For example, if we look at hydrogen B, we can draw a line directly to the right over to that dot, and then going down, straight down, we can draw a line to the carbon peak right below it. Now that signal is coming from the carbon that hydrogen B is directly bonded to, or it's coupled to, meaning that that carbon is carbon 3. Now looking at A, we can do the exact same thing. We can draw a line directly to the right to that spot and then go down, and that'll show us which carbon hydrogen A is directly bonded to. So that would be carbon 1. And from here, you can do the rest. You can do the same things with the other hydrogens. Just figure out which carbons they are directly bonded to and label the peaks accordingly, like I am showing here in the video. And that is it. We are done with this NMR. This is what it should look like when you are all done and ready to turn your NMR in. We have the molecules with the hydrogens and carbons all labeled, and then we have the peaks and solvents labeled as well. So you're going to do the same thing that we just did through this video with your other 2 NMRs for the Fisher Esterification Lab, and then all 3 of those will be submitted along with your lab write-up for Fisher Esterification, and together all that will be graded as your experiment. I hope this was helpful. You're going to be using the same tools and strategies to analyze the rest of the NMRs for every experiment that we do. So good luck and have fun with NMR.